Hello ladies and gentlemen, welcome to our class video about special right triangles. This is actually the first of two videos on that topic. We're going to start at the basic level of questions involving special right triangles, and then in a separate video I'll cover the more advanced versions. Our learning goal for this video is that you'll be able to apply the patterns of 45, 45, 90 and 30, 60, 90 triangles. Okay, so the first thing you're wondering is, what the heck with all of those numbers? What do you mean by those? We got 45, 45, 90, and 30, 60, 90. What do those numbers mean? Well, those numbers refer to the angle measurements of particular right triangles. So, a 45, 45, 90 triangle looks something like this. It's got angle measurements of 45, 45, and 90. Okay, 30, 60, 90 triangle looks roughly like that, and it has angle measurements of 30 and 60 and 90. Okay, so now you know what the numbers mean. Now, I called them special. What makes them so special? Well, they're special because of how they're related to other geometric shapes. A 45, 45, 90 triangle is half of a square. What do we know about the angles of a square? Well, they're all 90 degrees. If I cut the square in half by drawing in one of the diagonals, I will bisect two of those 90-degree angles, getting 45 and 45 there, and 45 and 45 there. Then the other angle is obviously 90, so a 45, 45, 90 triangle is half of a square. It also has another special name. It's called an isosceles right triangle. It's a triangle that has a right angle and has two sides congruent. That's because all four sides of a square are congruent. Okay, so what about a 30, 60, 90 triangle? Well, that is half of an equilateral triangle. Equilateral meaning all three sides of the triangle are congruent. Because all three sides are congruent, each of the angles are also congruent, so each angle is 60 degrees. If I cut one of those 60-degree angles in half by drawing an altitude, I would get 30 and 30. Then it would make a right angle with the base, or you could just make the angles add up to 180, and you have 90 degrees. So, if I cut an equilateral triangle in half down the middle, I get two 30, 60, 90 right triangles. Okay, so that's where they come from. But now for the main focus of this video, which is what pattern happens in the side lengths of those triangles. They're special not only for how they're related to other shapes, but there's a pattern in their measurements that if we can follow it, makes finding some of those unknown sides really fast if you catch the pattern. So focus here on the pattern. Okay, here's some 45, 45, 90 triangles. I want you to notice that all of them are isosceles. They have two sides congruent. I also want you to notice that each one is half of a square. On this left triangle, I've drawn in the other half so you could visualize the square. The side that we don't know on the 45, 45, 90 triangle is the hypotenuse. But it turns out there's a pattern in the hypotenuses. So we're going to find these lengths and notice the pattern. Now, how would I find that length? Well, so I know two sides of the right triangle, so we could use our old friend, the Pythagorean theorem. Now, I'm going to work out the Pythagorean theorem here, 1 squared plus 1 squared equals c squared, and so on and so forth. But don't focus there on the work. You don't even need to write all of that down. I didn't give you space on your notes, and I did that for a reason. I want you to focus on the results. The Pythagorean theorem there is just proof of what I'm showing you. So, if I do the Pythagorean theorem, we end up with a square root of 2 as the hypotenuse of that first triangle. Okay, remember that the square root of 2, just for reference, is some decimal number. It is a measurement that's approximately 1.414. We just write it in a different way because we can. Okay, I'm going to do the same thing on the other triangles. Okay, again, don't focus on the details of the Pythagorean theorem, but on the pattern and the results. So this next one, I'd have 2 squared plus 2 squared equals c squared. Notice that this answer could simplify. I simplified the square root, splitting the 8 into 4 and 2, and I get 2 squared of 2. Okay, what about the next one? I do 3 squared and 3 squared, 9 and 9, take the square root of the 18. I can simplify the square root, and I get a side length of 3 squared of 2. Do you notice a pattern yet? Got 1, 1, and a square root of 2, 2, 2, and 2 square root of 2, 3, 3, and 3 square root of 2. I wonder what this next one is. If you guessed 4 square root of 2, you're right. Here's proof with the Pythagorean theorem. 4 squared plus 4 squared, simplify the square root, yada, 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 and we get 4 times the square root of 2. Okay. So we recognize that there's a pattern in the hypotenuses of these triangles. Now, before we go on, again, I just want to remind you that each one of those is simply a decimal number written in a different way. We could convert it to a decimal using our calculator if we ever wanted to. Okay. In general, we will prefer the simplified square root version because it's more exact and we don't have to round. But it's there if we need to approximate. Alright, so we're going to build this pattern into what I call a formula triangle. Okay, this formula triangle will be applied to any side length on the triangle. So I'm generalizing the side length to be A. Okay, so that's any number could take the place of A. Notice that it's got 2 equal sides. It's isosceles, so I have an A on the other side. Whatever number is in one place has to go in the other. And what would go on the hypotenuse? What's the formula for the hypotenuse? Well, whatever goes there, I know it's going to have a square root of 2 in it. And then it's going to have some number out front multiplied by it. Well, what would it be? Well, it's just whatever number is in the place of A. So I'm going to call that A, square root of 2. You can see it as I'm going to recolor code the triangles that are on the left. So whatever number was in the place of A showed up on the hypotenuse in front of the square root of 2. You got 1, 1, 1 square root of 2, 2, 2, 2 square root of 2, 3, 3, 3 square root of 2, 4, 4, and 4 square root of 2. The next one, if A was 5, it would be 5, 5, and 5 square root of 2. If you can just recognize that pattern, whoo, it makes the question real easy because then I just know the answer. Let me show you that. Now suppose this is a 7 square root of 2 on the hypotenuse. Could you tell me what x and y are? If you paid attention to the pattern, then you could probably identify that those are 7. Now, I will walk you through the steps. Even though we already have an idea of what the answer is going to be, let me give you a tool. I want to illustrate the tool of radar again that we've talked about in class. And you may not have seen it if you're watching this video early. Those stand for read the question, ask what it's asking for, decode it, apply your knowledge, and check if the answer is reasonable. Okay, so read the question, find the values of x and y. Great. Okay, so pretty simple. It's asking for x and y. Duh. So I'll put x equals and y equals down in my workspace. In decoding, I pay attention to the details of the problem that help me know how to solve it. Because I noticed the 45 degrees, I know I'm going to need to compare this to the formula triangle. Okay? In using the formula triangle, I'm going to copy the formulas onto the question. So that side was A, so I'm going to put equals A next to it. That side was also A. This side has a formula of A squared of 2. So, what is A? Oh, well, the number in front of the square root of 2 is a 7, so A must be 7. If you need proof, you could divide both sides by the square root of 2 and get A equals 7. If you need me to show you that, but most of you could probably have seen it. So if A is 7, then that A is 7, and that A is 7, so x equals 7 and y equals 7. It would be 7, 7, and 7 square root of 2. Is that reasonable? Yeah, it follows the pattern that we know. It's just like it was 4, 4, and 4 square root of 2, this is 7, 7, and 7 square root of 2. Alright, not too bad. let's go on to the next type. So we're going to look at the 30, 60, 90 triangle pattern now. We'll do basically the same thing. Again, don't get lost in the details of the Pythagorean theorem. Each one of these is half of an equilateral triangle. You can see I drew in the other half of it there. Okay. The side we don't know is the height. I could find it with Pythagorean theorems. Here we go. Notice I'm having to subtract from both sides, and I get that side equals square root of 3. Okay, let's do it for the next one. 2 squared plus b squared equals 4 squared, simplify the square root, and I get 2 square root of 3 for the height. Think you know, see what's going on here? Alright, so 3 squared plus b squared equals 6 squared, subtract, square root, simplify, blah, blah, blah. We get 3 square root of 3. So are you noticing a pattern yet? Want to guess what the height of the next one is? I bet you can't. No, I'm just kidding. You probably can. So 4 squared plus b squared equals 8 squared, blah, blah, blah. Subtract from both sides. Okay, and we get b equals 4 square root of 3. I'm seeing the same thing that just happened with the 45, 45, 90 triangle. 3 square root of 3, 2 square root of 3, 3 square root of 3, 4 square root of 3. Yeah. Okay. Again, these are just decimal numbers. We could change them if we wanted to. We don't need to. Okay? But you always can if you want to in the calculator. We're building out the formula triangle one more time. We're saying that the short leg is any number. Okay, so this could apply to any triangle. What would go on the height? What's the formula for that side? It's going to have a square root of 3 in it, and the number in front is a. If you notice, 4 and 4 there, 3 and 3 there, 2 and 2 there, 1 and 1 there. Okay, whatever that length, the short leg a is, that's what goes in front of the square root of 3. What's the length of the hypotenuse? Well, if you look at the numbers 2, 4, 6, and 8, how are those related to 1, 2, 3, and 4? It's just doubled. So that side is 2a. Okay. Now we have a formula triangle that we could use to apply to a 30, 60, 90. Let me just show you how it works. We're going to look at one more example here, applying radar again, even though it's a simple question, I know. It's asking for the values of x and y, so I put x equals and y equals. The 30 and the 60 point me to using the formula triangle. So I'm going to just compare to this formula triangle. Okay, copy the formulas onto the triangle. I have to pay close attention to what angle the sides are across from. So this 30, across from the 30 is a, so across from the 30 is a. Across from the 60 is a times square root of 3, so across from the 60 is a times square root of 3. Across from the 90 is 2a, so across from the 90 is 2a. Okay, so let's start with the side where we actually have a number. Okay, so there's a 20 there. Alright, so 20 is 2a, so how many is 1a? Oh, well, that'd be 10. If I needed to, I could divide both sides by 2 and get a equals 10. That a must also be 10, so x is 10. That a is also 10, so y equals 10 square root of 3. Okay, we've got the answers already. See how quick that was? I didn't have to do Pythagorean theorem or anything. That's a lot faster. Make sure that you always leave your answers as simplified square roots. Know in your head that that's a decimal number that's just written in a different way, but we want to leave our answers as exact answers without any rounding as much as possible. So unless the problem tells you to do otherwise, leave it as a simplified square root. Alright, we'll go over some more examples in class if we need to, but hopefully you've gotten at least the idea of the pattern so that you can start applying it to some of these questions. Once you get the hang of the pattern, these questions go really fast. Alright, well, I'll see you in class. Have a great day.